Let's begin with a discussion of features associated with MemCache. Let's get our notes going. This will be Linux CBT MemCacheD edition. So, n number of features exist, as is typically the case with various packages that we study. However, let's take a look at, as usual in no particular order, some of the key features associated with MemCache. So what is MemCache? How does it help us? Why is it applicable? Why is it useful? Why are so many big websites using it? Well, it's a fast, multi-threaded, in-memory key-value pair store. So you can summarize it as an in-memory DB, but it's a key-value store. So key-value pairs, which can be used to represent data from disparate sources, including but not limited to SQL sources, such as MySQL, etc. So all operations are conducted in memory, and that's what makes it so key. And as a consequence, it provides us potentially with performance improvements or enhancements by orders of magnitude. So it's extremely fast compared to disk-based access. So potentially by orders of magnitude improvement over disk-based alternatives. MemCacheD falls into the category of NoSQL. So NoSQL or NoSQL category of DBs. So we don't use SQL manipulation language as well as definition language in order to store and retrieve data. So the library that's provided to access MemCacheD uses its proprietary sets of commands, which include getters and setters and so on, akin to other environments such as DBM and so on. Now, MemCacheD can accept on a per host basis and on a per instance basis an allocatable amount of RAM. So, in summary, that's an allocatable amount of RAM per instance. Usually an instance is tied to a host. However, you could have multiple instances on the same host. So it's possible to segment and run multiple instances per host. This is important because, for example, let's say you've got 4 gigs of spare memory. You could dedicate, say, equally 2 gigs to each instance, segregating the key value store. So it gives us a way to secure the distinct key value stores, or to provision, to segment them within memory, which provides some layer of security. And if you tack on the SASL supported authentication, then you could, in fact, weave in another layer of authentication, which makes each instance secure from the other, and different applications or different parts of the same application could access those particular stores. So let's just note that distinct instances promote security via segmentation. So that's a feature of it. However, we'll be using it largely as one instance per host, using some of the spare memory that's available. Now let's get into some of the interesting features that are perhaps more tangible. Essentially, you use MemCacheD and similar tools to offload your DBMS. So it offloads the DBMS, or your database management system. And this relegates, as a consequence, your DBMS to largely write operations. Or write operations, writes or write operations. Certainly, reads are performed, but whenever you're using caching technology such as MemCacheD, you read less, write more from the DBMS. So you perhaps read once per section of your application, which could be, let's say, a web page, a distinct web page, and its associated query. And then the rest is read from memory directly via MemCacheD. So As a consequence, you can significantly improve the performance of your applications as they'll bypass the DBMS, so long as, of course, the data or key value pairs exists within the cache at the time that it's called, of course. So as we've already mentioned, this facility stores key value pairs. So it's basically a key value store. And on the surface, this is a two-dimensional representation of data, but can be extended as needed. It's largely a giant hash table, which could include subsequent hashes. So MemCacheD stores hash tables, which can reference additional hashes to extend dimensions, for example. By default, we think of it as a two-dimensional hash representation. So default storage of keys and values, or key value pairs, represent 2D data. Basically, the name of, let's say, the column, thinking of it in SQL terms, and the representing value. Let's continue with some additional features. And so far as these data that are stored, the keys have a maximum of, or may be represented by a maximum of 250 bytes. This is your max. Unless, of course, the capabilities are extended. And we should just know that all characters are basically accepted, except white space or control characters. So that means we can, for example, hypothetically define a key to be the name of a file, which would include a dot somewhere to delimit the left from the right, or the prefix from the suffix, or the name from the suffix. The values may be represented by a maximum of 1 megabyte of arbitrary data. So, of arbitrary data. This means it can be anything. It isn't relegated to the constraints on the keys. So the keys are relegated to all but white space and control characters, and the data values can be anything. Can be binary, text, etc. Which means anything that's referenced from your site, let's say images, text, etc., may be stored in Memcache in values, so long as you're within the 1 megabyte range. And in general, Memcache is a distributed cache. Now, in its default implementation on one system, it's more seen as a distinct individual cache that isn't distributed. But once you extend the definition to include additional hosts, it immediately becomes a distributed cache where keys and values are stored across the cache as determined by Memcache and or by whatever algorithms you reference to ensure the storage of certain keys and values on certain hosts. But in general, if left up to Memcache, a number of key value pairs will be distributed more or less evenly across your distributed cache instances. But in general, it's a distributed cache. So free memory or RAM used across available hosts that are provisioned. Memcache uses, with respect to values that are stored within it, since caches are temporary, whether talking about a proxy server or Memcache or any other, let's say the caching of a table within MySQL or any other DBMS, they all have algorithms which dictate how long information is retained. In the case of Memcache, it's the least recently used cache algorithm that's used to determine what must be or can be forgotten at what point. So, in general, Memcache forgets LRU items first. This makes sense, seemingly. Least recently used cache. So the entries that are not used as frequently as Memcache needs space will be ejected from the cache. So let's just note, LRU items are ejected if necessary. If there's ample space, then it isn't necessary. Then the values should persist in the cache so long as their timers are still legitimate. And that leads us to the next feature, and that is These cached items have associated expiration times. The cached items are the key value pairs. So key value pairs. So you may define per key value pair timings associated with their particular entries, which will determine when they expire. And as a consequence, we'll be able to use them directly from memory during that time up until the expiration, at which point you'll have to, if necessary, repopulate the cache with the expired key value pairs. So, now of course there are global expiration times associated with all key value pairs if none are indicated or the defaults are used, but you can, on a per key value pair instance, mention the expiration timer, which will be honored accordingly. Another way to think of Memcache is that it provides us with the aggregation of, or the clustering of memory, which allows us to store key value pairs across hosts. So it also functions as a memory cluster, or gives us memory clustering services, which is essentially aggregation. And it does so for our key value pairs. So this means across the hosts that are used in your architecture, you can aggregate their free memory spaces using Memcache and then store various key value pairs across those particular participating instances accordingly. And again, this happens by default in a more or less even manner. So let's say you submit 10 keys to 2 hosts. More or less 5 keys or key value pairs will be on one host and 5 will be on the remaining hosts. So more or less it's an evenly weighted and distributed key value pair hashing memory clustering aggregation system. So let's just also note that key value pairs are distributed independently and more or less evenly across nodes or hosts. More or less, you can check the statistics to determine at runtime the exact numbers that have been distributed, but it's immaterial, as whatever memory is available to the hosts within your cluster will determine what gets stored where. And so long as nothing is approaching, none of the values approach or exceed or attempt to exceed the amount of available RAM, you should have few to no problems with the management of your cached key value pairs across the systems. The cluster works with members of equal or unequal weight. And by equality, we're referencing the amount of RAM available. So RAM available. So say, for example, let's just i.e. host 1 has, let's say, the default of 64 megabytes, which is the default when we install Memcache that's provisioned on the host. But let's say host 2 perhaps has a little more memory, maybe 512 megs. And maybe host 3 has somewhere in between, maybe 256 megs. This is perfectly fine. Perhaps for configuration purposes and for sanity, it helps if you provision an equally weighted system across your nodes, however many are a part of your cluster. But it will work with an unequal distribution as well. The hashing algorithm that's used by Memcache will determine that more key value pairs should be stored on host 2 as opposed to host 1, or opposed to host 3, and host 3 opposed to host 1, etc. So it'll sort that out for you. So you need not worry about the amount of memory that's available across your nodes. The idea is that you have systems in your environment that have free memory and can be taken advantage of, no differently than virtualization technology allows us to use CPU, RAM, and disk resources in a more efficient manner. Well, MemCacheD allows us to use free memory because oftentimes systems operate at less than full capacity, perhaps even a tiny fraction of full capacity, leaving or relegating resources to waste, if you will. So why waste these resources when we can store values in them and reference them accordingly at the speed of memory, with the only constraint being the delivery system, perhaps the network fabric itself. So the cluster will automatically allocate these values for you. But again, for sanity, perhaps you should distribute them. So note, for sanity, consider allocating weights. And that's your RAM available evenly, but it is not a requirement. Also, we should note that MemCache runs with very low CPU overhead. So this is key because your CPU cycles can then be spent on the more important applications du jour, if you will. So let's say we aggregate free memory from our web servers, which is one of the common models. Then the CPU cycles then should be distributed to the Apache or web server instances, and very little be used by MemCache. MemCache has very little CPU overhead, doing the bulk of its work in memory, maintaining these key value pair storages for us. It's basically a C server that's very fast, and it accepts potentially an enormous number of connections for those key value pairs via getters and setters and so on. So low CPU, so you need not worry about MemCache stealing CPU cycles from your key production applications. And so far as failover, that is part of the model, but this is client-based, which means you are to handle failover situations from whatever clients you use that are MemCacheD compliant. So you program for it, in other words. So basically, the standard model is if the results that you're looking for are not found in the cache, so that's MemCacheD, of course, then you consult the repository that stores the information, which is normally your DBMS, so repository of interest, which can be DBMS, for example. That's your standard failover-based mechanism for accessing these key value pairs. Again, you'll have a simple if block, and perhaps that if block's included across all of your, let's say, web pages, which is a common usage, or throughout your application. Again, if the key value pairs are not in the cache, and basically it's the keys. So if the keys aren't there, then consult the source repository, which may be DBMS, but it could also be your file system. So DBMS, file system, perhaps another database structure such as LDAP, maybe a slower mechanism such as DBM, etc. So this is your standard model. So that's how you handle failover. Because the argument, of course, is what if the keys are not existent because they have yet to be loaded, let's say, by a first call to the web page or to the application. Or perhaps there's some sort of corruption with MemCache. Maybe it isn't running for some strange reason. Or maybe one or more values that are of interest are not present. So simply consult the original source for that information, which is usually a database. Let's also note that MemCache is great for dynamic data that changes infrequently. So if it doesn't change frequently, how can it be dynamic? Well, it changes infrequently, which promotes reads versus writes. Now, that doesn't mean we can't store or write information quickly to MemCache. We certainly can because it's in memory, so it's really the speed of memory minus the overhead of the server itself, MemCache. So it's fast, as well as the network I/O that's usually involved between the client and the server, unless you're operating locally. However, the idea is that for your applications, which generally tend to be web pages, you should store in MemCache information that doesn't change that frequently. If it changes very, very frequently, then perhaps MemCache isn't the place for you. Perhaps a more transaction-oriented environment, such as a DBMS is. So let's note some examples, maybe site metadata. So it could be, for example, let's say for even our site, let's say the number of hours associated with a product, its price, maybe the syllabus or syllabi across products. That would be considered site metadata. Maybe some other pages like contact, about us, items that don't change often, maybe a client list, etc. Perhaps for a Web 2.0 social site, maybe profile information, as in the case of, say, Facebook, for example. So a user logs in, and certain data tend to be more or less consistent. The user's name, so profile information, name, perhaps photo, alias, etc., tend not to change rather frequently. So site metadata, and for us, let's just note some examples as perhaps maybe contact, about us, syllabi, etc. These items don't change frequently and should be stored perhaps in a fast location as opposed to the file system. Now you may ask, well, why consider Memcache, considering nowadays hard drives are fast, Linux systems generally are fast, and the website appears to operate with great efficiency because whatever load testing you've done seems to communicate as such. The idea is really the inability of hard disks to scale, as well as databases to scale with large numbers of simultaneous connections, or the great variety of potential clients connecting, let's say, from mobile as well as desktop and other traditional means. So the idea is that nowadays, since everything's connected to the net, requests are made largely with HTTP. If those requests are constantly channeled to disk, then at some point, at some margin, you'll begin to realize degradation in performance. So the idea there is you won't be able to scale beyond even the fastest disks. So one option, of course, is to buy faster disks, to RAID the disks, to construct them in such a way where reads are optimized, but it'll never approach a speed of RAM or a facility that can take advantage of RAM. So this is why we use caching, especially for large-scale operations. But you can use it on a small-scale basis. For example, we use it for the information we've listed, such as syllabi, about us, contact, the client list, etc. It's all coming out of Memcache. It doesn't have to. The database is fast enough, but it's even faster when it comes from Memcache, for example. And any changes are handled automatically upon writes to the database. Let's note some other features. So as we've mentioned, getters and setters. So Memcache, of course, supports what you could summarize as storage and retrieval commands. Basically, your getters and setters. The daemon itself facilitates these storage commands, no differently than, say, MySQL D, that is, or MySQL server. And some of those commands include, for example, get, set, add, etc. And perhaps we'll just break these out just a little bit. So just to give a little more definition as to how they work. They're self-explanatory, however. Let's just include them as per the documentation. So the get command obviously gets information. So this retrieves key value pairs. So you get a key, it gives you the value. No differently than selecting a given column from a table and its value is returned, or the values across the rows are returned. And set does the reverse, of course. It stores data, possibly overriding existing data. So set is absolute. Regardless of whether or not data exists, will cause a new write operation to overwrite the existing in-memory representation of that particular key value pair. Add stores data if it doesn't exist, and that's a cautious approach to the storage of data that perhaps is not so dynamic, is more or less static, but perhaps one or more snippets of your code simply need to double check whether or not it pre-exists before determining whether or not to perform a new write. So if you'd rather be cautious, use the add as opposed to set. So this is the cautious approach to data commits to your Memcache instance or instances. Replace is another command, and again, it's SQL-like in the sense that you've got ways of adding, removing, updating data. And this stores data if it already exists. And that should be implied by its name, replace. So a failure will result in the event that the data or the key that you're attempting to update does not exist. You've got append. Well, this adds to last byte of the existing value. So if you've got 4 bytes and you're adding 1 byte, you'll have 5 bytes. That 5th byte appended. And then prepend, which of course does the inverse. So inverse of append, which prefixes your data with whatever number of bytes, or prefixes the first byte with whatever number of bytes you present. And another popular memcache semantic is cas, or compare and swap. And this, if the data has not changed since we read it last, will perform the swap for us. And this provides us some means of, in a sense, transaction-oriented communications. Let's just go ahead and save this. And we'll be looking at each of these major commands, of course. So this is memCacheD addition notes.text. So these are your common commands which allow us to store, retrieve, etc. Now we still have some other features in mind. Again, memcache can be used in so many ways, and it provides us with a considerable number of features that are so useful. It is horizontally scalable, and this we've alluded to, and that is because you can add n number of hosts indefinitely. So you may add n number of hosts indefinitely, or infinitely, if you will, more or less. So as your architecture, your application grows, and as you take advantage of, let's just say, cloud services, so cloud services, perhaps AWS, with hosts distributed across the globe, you can then extend your memcache cluster accordingly. So you could potentially have these hosts through AWS or any other web service distributed all across the net. And so long as the connectivity is good between them, then you can have the cache available across the globe and have your application consult the data accordingly. And that way you, of course, have geographic fault tolerance built in. Perhaps you'll lose portions of your cache if there are issues with geography, data centers, and so on, but they can always be rebuilt with a simple conditional block. So let's say you've got servers in the United States and Britain, and perhaps, let's say, in the data center somewhere in the US, that cache, that section of your cache is lost. Well, certainly the code that runs looking for those key value pairs will have to rebuild those data sources from perhaps the DBMS. And the DBMS you would replicate as well. So maybe you have MySQL running in each data center replicating information between the two. So you'd have some cache misses in the event of problems with geography, electricity, so on and so forth. But that's outside of your control, and you just have a performance hit for a short period of time. So that's not a big deal. So it's basically infinitely horizontally scalable. There are no limits to the number of hosts you may spread across your memcache cluster. And with that said, we should also note that the individual nodes themselves, or individual hosts or servers, do not, unlike many other daemons, communicate. And that's important. So truly you're maintaining distinct partitions. Let's just note distinct key value pair partitions. So how can this possibly be useful if they're not communicating, as is the case with traditional DBMS architectures? Well, it is useful because you spread, let's say you've got 100 servers and maybe 1,000 key value pairs, well, maybe 10 on each. And they're not related, but they are. It's your application that weaves them together as needed. You can group key value pairs and force them to be on certain servers if necessary for performance reasons. But apart from that, the key value pairs are simply distributed out in the ethos across your Memcache cluster instances, and then your application weaves them together as needed. So these individual servers do not talk to one another. Memcache supports multiple gets. This is a way of fetching a lot of information in one swoop, if you will, parallel fetches of information. And of course, these are key value pairs. So key value pairs, we refer to this quite often because that's essentially what you use it for, from multiple servers in fewer operations than, let's say, single gets, if you will. Single gets, or simply a get. So through multi-gets, we can pull in a number of key value pairs in one operation, or fewer operations than, say, individual operations across all your key value pairs, across all of your servers, of course. So the server stores the data. We've mentioned the client queries the server, so server stores data, and these are your key value pairs. The client, whatever the client happens to be, and that can be anything from a web application to a desktop application to a mobile application. And the client, if programmed properly, scans or queries the appropriate server for data. And by appropriate, well, the hashing algorithm tells the client where to fetch the data from. So hash algorithm tells client where to gather data. So this is all determined by the client and the server. They sort out where key value pairs are represented. Let's just also note that insofar as client communications is concerned, MemCacheD integrates with common languages which function as clients, such as PHP, Python, your typical Perl, Ruby, etc. So whatever your application happens to be written in, Java, etc., there is bound to be a MemCacheD client to talk to it. And there's always the basic live MemCacheD, which basically any client can talk to take advantage of Memcache services. Insofar as TCP sockets, it binds to TCP, by default that is, 11211. So that means for you firewall administrators, you should provision accordingly. It does provide us with a text-based interface on that socket, so it's accessible via telnet, which means you can talk to it. So i.e. SMTP, for example, HTTP, etc. So you can perform gets and sets via the telnet interface, which of course raises security issues. And let's just note that the default configuration does not implement SASL auth. In fact, it implements no auth, which means you should consider where you place your MemCacheD instances and determine what security should be wrapped around it accordingly. So you'll often find that these Memcache instances are implemented within DMZs that are protected by a firewall. So the Memcache port tends not to be published to the internet. If published to the net, then you should use SASL authentication, because otherwise anyone can interact with your cache, changing data accordingly so long as they figure out your keys, and that could corrupt your application. So let's just note that as well, that if MemCacheD is published to the net, you must use authentication, or you should use auth. So use SASL auth, and perhaps otherwise malicious users could change key value pairs, which could corrupt your applications. So protect Memcache accordingly. Run it. Let's just note as well, typical deployment of MemCacheD is in the DMZ. And in this case, let's just know, in the DMZ with TCP 11211 restricted from net access. And perhaps even from your internal user community as well, rendering it simply accessible by the nodes that are of interest, such as the other web hosts that are part of the Memcache infrastructure and your overall, let's say, web application, but it could be any type of application. And again, insofar as authentication, there is auth support with SASL. And perhaps we should just note that this adds a level of latency to queries. So you'll lose some performance benefits with the usage of SASL, but this is absolutely important, especially nowadays with cloud environments such as AWS. Your servers could be all over the place with IPs that are accessible to everyone, and that is not a good solution for Memcache, as anyone, including myself, could access your keys, make changes, corrupt your application, etc. So use SASL auth if you're in a cloud or net published facing environment. As far as our architecture, let's take a quick look at our drawing to see what's of interest. That's MemCacheD edition. That's this. It's your standard architecture. We don't veer from it. We keep it simple. 7050/24 is the network. But the servers that we're using, more and more lately, we've been doing a lot with Ubuntu because of its updates. It's the distribution du jour. So we're working off this box, UBUDES 192. That's this system here where we have our nodes. And we've got some other systems of interest. We've got 3 Ubuntu servers, Linux CVT Ubu serves 1, 2, and 3, situated at IPs 110, 111, and 112. That's these 3. Then we've also got a Debian box, which essentially is Ubuntu. They're one and the same, which is at 102, which is Linux CVT build 2, which has a MySQL instance from which at some point we can cache key value pairs and perhaps even have it join the Memcache cluster. But ideally what we'll do is construct a Memcache cluster out of these 3 nodes, Ubus 1, 2, and 3, or Ubu serves 1, 2, and 3. We'll initially start with Ubu serve 1, get a feel for Memcache, and then introduce 2 and 3, potentially the Debian hosts, interact with SQL, do a little bit with PHP, so on and so forth. So our desktop window is this system, UBUDES 1. We're talking to these 3 guys and occasionally this one, Debian, as needed. So let's close this out and continue.